Dear all, first of all, I would like to thank you for attending this presentation and for giving us the opportunity to present our research work. Today, I'm going to speak about performance analysis of x86 and ARM-based instances with one use case application or enabling technology in mind, and that's video encoding. You already know that many applications rely on video encoding as an enabling technology to efficiently provide their services. Now let's start with the introduction itself. As I already mentioned previously, video streaming is enabling technology and it's undivided part of the internet network. It enables us to consume multimodal digital media. In this case, I mean video streams, audio streams with very high quality. And as you are already aware, multiple essential services rely on video streaming to convey information. This is, for example, traffic control to see if there are traffic jams somewhere, or there are some, for example, there are some car accidents or something similar. Then also this could be used for crowd controlling, for security surveillance, and many other essential operations. But furthermore, taking into account all these essential services, there are many entertainment services that rely on video streaming. You already know multiple platforms like YouTube and Netflix that provide us on-demand video services through which we can watch some entertainment. But not only that, this is also important in the let's say in the information industry. I would say more, let's say, televisions, radios, through which we also get informed. And many times now, video streams or video streaming technologies used so they can provide these services to us. Now, I think before going any further, it would be essential that I tell you how this process works. Let us analyze this slide. You can see that on this side, we have the video sources. That's this video camera that provides a raw video stream. This raw video stream is with the original resolution as the camera itself created. So that's why we use a specific software called codec to first divide the video stream, the whole video stream, into multiple smaller segments or chunks, and then all of these smaller segments and chunks to encode them with different resolutions and bit rates, means with different sizes and bit rates. And then if it is a live video stream, we provide this information directly, or the video stream directly to the end user devices. So if this is, for example, for video on demand, this information, of course, will be stored in a database. And now, maybe after, okay, this was a very simple way of explaining how the process is done. Maybe now you have one very important question. Why do we need to segment or chunk the raw video into multiple small pieces? Why do we need multiple resolutions of the video? Why do we need multiple bit rates of the video? So I will explain more about that in the next slide, which is our motivation. Unfortunately, as you know, the internet network connectivity is not always stable. The bandwidth can vary depending on where you are. Then we have heterogeneity of devices where we can use powerful desktop computers to consume our stream, or maybe some older types of mobile phones, which might not be able to, let's say, play that video, or maybe the connection is so bad that it cannot be transferred on time. In order to solve these issues, the so-called HTTP adaptive streaming was introduced, which is a technology that applies all the methods that I told you previously. So encodes the video content by dividing it into small segments and then encoding in multiple so-called bitrate resolution pairs so that it can adapt to varying bandwidth fluctuation. Meaning, if it is detected that your network connection is currently slow, a segment with lower bitrate and resolution will be sent to you. But this segment will be probably between 2 and 10 seconds long. So after that, another check will be done. If your connection has stabilized, then we can send you information with higher resolution. And this solves a lot of our problems. But you should be aware that HAS is compute demanding and thus requires a vast computational resources, which currently, of course, are provided by the cloud. But this does not solve our problems because, as you know, that the cloud providers can offer a large set of resources with different architectures. Now, you know, with the popularity of ARM, now we have x86 and ARM instances, and there are many instances with different capabilities and different prices. And we don't know how, let's say, Amazon offers like hundreds of different instances optimized for computing, for memory based on the different architecture, and then all of them have different prices. And it is therefore very difficult to choose the most appropriate cloud resources for performing HAS encoding of the video. And as you already see, for a company that provides such a services, so video streaming and encoding services, the decision could be very difficult because choosing inappropriate instance that has not enough resources can lead to low performance, and then all your clients are leaving because they are dissatisfied. Or on the other side, the other issue that can happen in this case is that that you choose a very powerful, very expensive instance, and then you cannot make any profit. So that's why we come to our goal. In order to solve this issue, or to make this decision easier for the practitioners, but not only the industry practitioners, also this is widely used in academia for providing now video lectures and everything. So both for the knowledge sharing and for the industry, we decided to evaluate the relative video encoding time and cost for different instances and different families based on the x86 and ARM processors. And we would like, under 2, to identify the fastest and cheapest instance type among all of the instances, so we can give a clear recommendation. And we would like to do this for different presets, as I told you, for different instance families, different bit rates, and different encoding techniques. And with that, to compile a set of recommendations that could be directly used by the practitioners, both in academia and in the industry. And what was our vision? How to achieve these 3 goals that we set up? Before trying to do all of these things, you know, to compile the recommendations as our main goal and to perform the evaluation, the performance evaluation, we have first to create evaluation methodology, and of course after that experimental design. But let's start with the evaluation methodology. We divided our evaluation methodology, as you can see here, in 2 phases. Phase 1 encompass encoding data generation, which describes the selection of the video sequence, then the video codecs, the encoding parameter, and so on. And the second step that we have here, this one is more focused to the cloud. The first one was the video encoding focus. Second, to the cloud, is how to select a proper instance and microprocessor architecture. So what we did with the first step, or the first phase, sorry, encoding data generation, we have 3 steps. The first step is choosing video sequence selection. We choose video sequences different for our evaluation from 2 to 10 seconds as recommended by the best practices in the industry, and with accordance, of course, with the codecs. But then you ask, which codecs do we select? We selected X264 and X265, both put together in the FFmpeg video framework, because these are the most widely spread codecs, and we found report from industry that they are used by 90% of the video streaming industry. So they are very representative, and it would be best if we use them. After deciding the video sequence selection with codec selection and which package to take, of course, we took here the FFmpeg framework that contains multiple libraries and tools for managing videos. And from there, we choose appropriate set of encoding parameter selection, because I told you, usually we have multiple pairs between bit rates and resolution. And with this version of FFmpeg 4.3. We have 19 different bit rates to resolution pairs that we choose, and you can see them here listed. And of course, we perform evaluation for each one of them. Now we go to the cloud part. What was important in the cloud part? I told you that we'll explore multiple different instances. But it was first important which microarchitecture to choose. And you can see from the title, of course, it's clear to you that we went for x86 and ARM architecture, which are the only two available currently. But then we did further exploring, and we realized that for the x86, it would be very representative if we take the biggest players here, and that's AMD and Intel. So we choose from x86 Intel Xenon Platinum processor, which is a multi-purpose processor, and we took instances covering, as you can see here below, covering both the first and the second generation of the Intel Platinum 8000 series processor. Then from AMD, we choose similar C instances, again, as you can see, with similar memory, same memory, same virtual CPU, similar network connection, and so on. But for AMD, we choose the EPIC processor, which is based on the either first or the second generation Zen architecture, and this could give up to 64 concurrent threads with 32 cores. Lastly, from the ARM side, you know that for server processor ARM, it's primarily now focused on mobile processors. Now, as you already know, that Apple started offering desktop versions. Qualcomm offers such versions, I think, for almost 1 or 2 years, but maybe not with the same performance like the Apple M1 chips, but they are also advancing. Google has same plans and so on. But in the server area, I think the biggest player is AWS, that create their own version. So they created a 64-core monolithic server chip called Graviton 2, which is based on the Neoverse N1 cores, based on the Cortex A76 cores, which are the most powerful currently. And all of them are optimized in the current package created by AWS for server applications. If you want to check more about our instances, you can see here below based on the instance type. After explaining our methodology, now the next step that I have to provide you information is about the experimental design. So what are we going to evaluate? First of all, before doing anything, of course, we have to define the metrics. So the first thing here that we will need to define are the metrics. So we compare, in this case, ARM instances with the Intel and AMD instances, and we define 3 metrics. Relative encoding time, which is the encoding time difference between x86 and ARM for encoding video segment V with a bitrate B and a preset P. Then is the encoding cost, but this is the exact encoding cost. So this means how much is the cost per second in US dollars for doing encoding on a given video segment. And then is the relative encoding cost, which of course uses the encoding cost itself to find the difference between the x86 and the ARM instances. After defining the metrics, we define our experimental design. So our experiments, we created 2 sets of experiments, let's say in that manner. First one focused on the instance family, where we try to find the relative encoding time difference and the relative encoding cost difference across all processor architectures. So x86 and ARM for different instance type. Be aware here, instance type. And then we go step further in our second scenario, where we check the fastest encoding time. So here, not the relative and encoding time and cost, but the fastest cost and the fastest time per architecture. So here we don't look the instances, we put instance types aside, and we look only at the architecture. After presenting the evaluation methodology and the experimental design, now the next step is to check the results and try to create a set of recommendations out of them. So the first evaluation results that you see here is the relative encoding time and cost for different instance families. Under A, or in the upper part, you can see the comparison in encoding times between, as you can notice at the upper part is comparison between Intel processors and Graviton processor. You can notice the difference because the Graviton instances end with G. This is in the upper part. In the lower part here, you can see comparison between the AMD instances, which end with A from AMD, and G here from Graviton, the same. And here, we mark with color. When you see somewhere red color, that means that the x86 instances in both cases are faster. If you see color like at least light blue, dark blue, and so on, it means the opposite. It means that in this case, those instances are slower. In the other case here, you can it's the same trend, the same coloring trend, but here it's focused on the encoding costs that are induced. So we can immediately notice after analyzing this that for fast encoding, we always recommend using x86 instances, especially for bit rates below 7,500, which are done with the presets ultra fast and very fast, because you can see in all of these cases in the bottom parts, it always these lighter or reddish colors in majority of the cases. So we will in this case recommend for the encoding time, we recommend the x86 instances. The ARM instances are very fast for bit rates higher than 7,500 bit rate, bits per second. So we can notice that in those cases, in majority of those cases, and especially for presets very fast and fast, we can notice that the biggest benefits come from this case. But of course, as always, we have some exceptions. We can see, for example, in this case, with the C5 instances, the AMD CPU gives the best performance benefits, which could be up to 60% faster than the ARM. So if you would like to use C instances or computing instances, then we recommend AMD over ARM, or also Intel over ARM. And then when we go to the cost, of course, we can see the same trend. We have, again, for many of the cases, as you can see, these blue tones here, dark blue tones show us that we could have up to 40% savings in encodings, but not in all cases. Let's say, like we see here with the C instances, again, we have the same trend, meaning that it's much better to use AMD over Intel or ARM CPUs. We said now, let's see the performance of ARM for, I didn't mention, for the X264 codec, it's very good. But now let's check step further to see which instance is the fastest out of all these ARM instances and which one is the cheapest. We can see that for the majority of cases, the memory optimized instance is fastest compared to all other memory optimized. And in some cases, for small bit rates, could be the air type of instance. On the other side, for the cheapest, you can immediately notice this is almost called light gray. It's the T4G instance. This means that this is the burstable instance. So if you would like to have the lowest possible price because the ARM gives that, just take T4G. If you want faster performance and you would like to use ARM, then just simply take M6G. But if you would like the fastest encoding time, maybe AMD would be the best option, and in some option that would be also Intel. Now we go further for the X265 codecs. We see here a different picture. We see red much more, and be aware that in this case, this scale start previously was from -40 to 60. Now the scale starts from 0 to 700, meaning that if you see blue, again, the x86 instances are much faster. What that means, in this case, it means that these instances perform much better than any ARM instance. Why? What is the case here? You can see that in some cases, the ARM instance did not finish encoding, or it was 700% slower. And what is the reason for that? The reason is optimization. Actually, we believe that it's optimization because the new x86 codex is not fully optimized for ARM. We, in this case, use even a special optimization from Huawei, and this again did not help a lot. But take into account that this is a snapshot. We want to repeat this experiment next year, and we hope that then there will be optimization and we can solve this issue easily. Now, out of all these results, we created an evaluation summary, meaning like recommendations for the practitioners. And you can see, if you use X264 for fast encoding, please use AMD instance or maybe M6G for ARM. For low cost, always ARM. But for X265, use always Intel for now, at least until new version of the codec comes. And then to further help this step, we provide here comparison between multiple different instances, comparison between all these different instances, which one is at the top part fastest and which one is slowest. So you can, and then which one is the lowest encoding cost. And you can immediately notice that the C instance, if you want to use C, use AMD. If you want to use M type of instance, in many cases, Intel is the best, but in some cases you see here ARM and in very few cases AMD. But for the lowest cost here, as you can, and this is fully focused on upper part, this is focused on X264. You can see that for C is AMD, for everything else related to the cost, the ARM is winner. So, after giving this summary for the practitioners, I would like to conclude this presentation. And this presentation we provided, as I explained, performance analysis for video encoding tasks, giving comparison between ARM and x86 instances. We concluded a total of more than 20,000 different experiments for the two scenarios that we had, and we compiled a set of recommendations for the practitioners, both in industry and also for people in academia. In future, due to the problems that we had with X265 or ARM problems with execution, we plan to extend our analysis with different emerging codecs like V9 or the new version of X165 in order to be able to better generate our recommendations. With this, I would like to thank you for your attention, and I would now open the question sessions. If you have any questions, please ask them now.